let's start where we stopped last time. I'd like to do another example of a framework in the plane. And this is kind of the famous triangular prism framework. You can see it pictured here. It's got two triangular faces, and they're connected by three bars. And we'd like to study the pure condition. Remember, that's a polynomial in the brackets that vanishes when this framework has a motion, has an infinitesimal motion that's not a rigid motion, and this framework is isostatic in the sense that it's generically rigid, but in special positions. Then where the pure condition vanishes, we're going to find that it actually has motions. And so what we do, as before, we tie down two of the vertices using three edges because we're in the plane. And you can think of saying that A is a fixed vertex and B is kind of constrained to lie in a one-dimensional space. So we've removed both translations and rotations from our consideration. And then we write down this extended rigidity matrix. And there's a bit of a convention here that I want to remind you of. A minus x refers to the position of A minus the position of x. And the positions of A and x are in R2. So A minus x is really a 2 vector. So it's spread across two columns here. So this is a 2 by 2 matrix here in the top left corner, and then you've got the rest of the matrix here. And it's got a nice diagonal structure, block structure here. And so its determinant is the determinant of the top 2 by 2 matrix, which turns out to be equal to the determinant of a certain 3 by 3 matrix, where A is one column, X and Y are the other two columns. Okay, so that's one of our brackets. This next 2 by 2 matrix is another bracket, A, B, Z. The second, third matrix here is the determinant A, B, C. And then we have the determinant of this big portion in the bottom right. If you look at that for a while, you'll realize that this determinant here is actually the determinant of, it's the pure condition for a triangle with 3 tie downs. Well, maybe not the pure condition, but it's the full determinant of MGT, where G is just a triangle, and you've got 3 tie downs. So you've got DEF as a triangle, and D is tied down to A, E is tied down to C, and F is tied down to B. And what we know is that such a determinant, such a polynomial, is going to be given by the pure polynomial for the triangle, which is just DEF, and then we multiply by the portion of the pure condition that refers to the tie downs. And usually we factor those out. These are these black things here, the brackets that we factor out. But here we're not going to factor them out. Because we're actually interested in the whole full determinant. And that determinant, that portion of the determinant is encoding when the tie downs are dependent as lines in projective space. So the tie downs DA, this bar, CE, this bar, and BF, this bar. When are they dependent in P2 as lines? Well, they're dependent in P2 when they're coincident, when they intersect in a common point. And that's one of the things that we developed a bracket condition for last time. We actually wrote down that bracket condition directly. And so this was the bracket condition. And so we can just put that in as the rest of the determinant. And so you get this expression here. that determines when you have an actual motion of this isostatic framework, which I think is pretty cool. Okay, so I want to just talk about a few generalities now, which I find very interesting. These are things that I learned from Walter's paper with Tony and Bernd, the survey paper that's out on their website now. So if you have a framework in, let's say, n space, so this is G sitting here in the, I've drawn it like a plane, but I'm thinking of it as n space. Then, and if you take a vertex outside of Rn, so think of it in Rn plus 1, then you can kind of join that vertex to all the vertices of G, and we call that new framework the cone over G. And White and Whiteley proved that coning doesn't change the rigidity of a framework. And in fact, you can even slide these vertices that are currently in Rn, you can slide them along their kind of coning lines as well and still preserve the rigidity, I believe, which is super cool. Okay, so I guess what I want to do next is I want to address how does coning change the pure condition, and it's very simple. If you've got the pure condition of your framework G in Rn, and you want to find the pure condition for the coned setup, then all you have to do is in every bracket appearing in CG, you just tack in an extra V inside that bracket. You make the bracket one bigger, and that's it. And this is assuming that that the vertex that you're coning over, that it remains fixed, so that there's no infinitesimal motions of that vertex that are allowed. It's somehow tied down. And I'll say that Jessica Sidman and Ashley Wheeler and I found a way to consistently cone not just the bracket expressions, but the Grassmann-Cayley factorizations for those bracket expressions. And I won't say too much more about it. It's pretty simple. If you've got a join of a bunch of elements, then you just tack on an extra V as an element of the join, and you get a new Grassmann-Cayley expression that refers to the join of V with these guys. And if you had a meet of two extensors, X meet Y, then you do this extra little bit. You do X meet, and then the thing you meet with is the join of Y and V. Okay, I'm going to skip actually the application of that. I'll just say that what we did for that was we wrote down Grassmann-Cayley expressions for brackets that characterize when d plus 4 points lie on a rational normal curve. So if you know what that means, great. If not, then maybe you've heard of the twisted cubic in P3. That's a famous curve in 3 space. And you could ask, when do 7 points lie on that twisted cubic? And this characterization is quite nice. What do? You take, fix one of the 7 points, so pick that, and cone over that point to the other 6 points, and project those lines that you get joining the points, and take those lines and intersect them with a hyperplane, with a plane. And you get 6 points on the plane. And the 7 points that you started with lay on a twisted cubic if and only if the 6 points that you get lie on a conic. And you can then, you know, Grassmann-Cayley expressions to check when 6 points lie on a conic from Pascal's theorem. This has to happen for all the different projections. There's 7 of them from 7 points to the other 6. And this characterizes when 7 points lie on the twisted cubic. And we did this in all dimensions, which is kind of cool. And the work leveraged work by Caminada and Schaffler, who worked at the bracket level, and we worked at the Grassmann-Cayley level. Okay, I did say something about this, so anyway, that's all I want to say. Okay, but similar in some ways to coning is a much kind of reduced kind of coning, the zero Hannenberg move that we've talked about before in lots of talks. So if you've got your framework G here, and you want to add in a vertex in a zero Hannenberg move, just add this extra vertex and join it to two other vertices by edges. Zero Hannenberg moves preserve rigidity. And you might say, well, how does the pure condition change? And it changes in a very nice way. You just, it's just VAB for this triangle, right? Yeah, anyway, so it just multiplies your pure condition by an extra factor, one extra bracket. And I thought for a little while that, well, it should be easy to work on one Hannenberg moves too, right? Like how hard could it be? Turns out it's pretty hard because essentially if you could understand how pure conditions for one Hannenberg moves work, then you would understand like the full situation of rigidity certainly in the plane and in other places too. So to some extent, so this is actually, I think, harder. So we're not gonna delve into that right now. So it could be an interesting project. Okay.
Will, can I ask a question?
Yeah.
What do you mean by zero Hannenberg and one Hannenberg? So a zero Hannenberg seems to be you have an edge and you add a vertex.
That's right. And a one Hannenberg is
that you just add a vertex connected to two others, or is that a one extension?
It's a one extension. That's what I mean by, I think you've got an edge and then you connect, you draw three new edges.
Okay, so that's usually called a Hannenberg 2, I think.
Yeah, so just Will, again, do you need that edge between A and B?
Yeah, that was going to be
what do you call the zero Hannenberg extension?
Yes, you'll need that.
Okay. So it's not just some two vertices. Okay.
No,
so
I think it's
slightly stronger.
You have to start with an edge A, B, and G. Otherwise, you don't really get a triangle here, and so
that's right.
It really makes sense.
Yeah.
Okay.
Yeah.
Good point. Sorry, I think I probably misstated that. And maybe I'll just I'll dodge Sean's question for now because I'm not sure exactly what I mean by when Hannenberg moves. But I guess I mean that
an edge split or a
result about infinitesimal rigidity in the plane, that it's preserved by these two moves, zero Hannenberg moves and one Hannenberg moves, and that you can kind of build up every rigid graph from like essentially a line segment by a combination of these moves.
You need something more general than the zero Hannenberg that you got here. You need to be able to add a vertex connected to any two vertices, not just it doesn't just have to be connected by an edge. It has to be slightly stronger, slightly more general.
So even here, I think things are more complicated. Although I think it's maybe worth trying to like understand like how the pure condition behaves for zero Hannenberg moves.
Is anything known at all, or
not by me?
Okay.
I'm already on thin ice here. I'm gonna. All right. Yeah. This is where I'm stepping out just a little bit beyond what I've read in the literature, and I'm getting in trouble. So
no. I'm guessing probably nothing is known, because I think you are right. The triangle does make things very nice and doable. So that does seem to be the key element. Anyway, thanks for answering my questions. Thank you.
Okay, no problem. Okay, so we could go on. I've got two other examples, and these are in three space. So now we're shifting up to spatial structures, and so I thought we'd start with the tetrahedron. And there's two ways to do the tetrahedron. One is to say, hey, the tetrahedron is a cone over a triangle. And we already figured out the pure condition for a triangle. So can't we just tack in an extra vertex for the cone vertex and into our bracket for the pure condition for the triangle, which is ABC, and then you'd have ABCD. We'd be done. And that's true. Alternatively, you can do it from scratch. You could tie down A. You need 3 tie downs to tie down A in 3-dimensional space. And then you get 2 tie downs on B and 1 tie down on C. And then you get actually a block upper triangular matrix for the extended rigidity matrix, or augmented rigidity matrix, as I was calling it. And then you can calculate what the determinants of all these matrices are. And just like before, when we had 2x2 determinants that also had the same values as 3x3 determinants, here I've got a 3x3 determinant that has the same value as a certain 4x4 determinant, whose columns are A, X, Y, and Z. And these positions of A have 4 entries, because now we're in 3-dimensional projective space, right? So there's 4 components for A. Or you can think of A as just being like the X, Y, and Z coordinates, and then a 1 tacked on if you want to kind of place everything in the finite part of the projective plane. Okay, so this is like the simplest example. Let's look at the next simplest example, which is not so simple, which is the prism, but in 3 dimensions now. So in black, I've kind of drawn that prism. There's one of the triangular faces, ABC, and I've got the other triangular face, DEF here, and they're connected by 3 bars as before. But that's not isostatic in 3D. If you take 3V minus 6 here, it's not equal to the 9 edges, it's equal to 12. So we have to add 3 bracing bars in order to kind of brace the prism so that it becomes rigid, or generically rigid at least. And so I put these 3 red bars here. I've joined A to E, C to F, and B to D. And now I've got a isostatic framework. So it's generically rigid, but in some special positions, it might admit non-trivial motions. And we just go ahead and we tie down A, and we tie down B, and we tie down C. We need 6 tie downs in 3 space in order to kind of eliminate the 6 rigid motions. And then we write down the augmented rigidity matrix. And we get something, again, in block triangular form, but unfortunately, it's a little bit tricky. So here, you get just the usual 4 bracket for a tie down, and here's another 4 bracket, another 4 bracket, and these are kind of things that are relatively easy to see from the block structure, and they're also the portion of the pure condition that we're going to throw away because it's got tie downs in it. So really, we're interested in the determinant of this lower right matrix, and unfortunately, this doesn't have a block structure quite so nicely, and it's not possible to reorder the rows so that it does have a block structure. I tried. So things are problematic here. So how are we going to find the determinant of this lower right matrix? Well, again, if you look at it closely, what you find is that it's the augmented matrix for this triangle DEF, where each of the points D, E, and F have been tied down to 2 other points, like this. So I've got D, E, F, and then I've got A, now thought of as a tie down vertex, and it's connected to D and E, and B is a tie down vertex connected to D and F, etc. And what we'd like is actually the full determinant of the augmented matrix for this, right? That's the lower right matrix. and what we know is that it's the portion of the determinant that comes from the tie downs times the portion that comes from the pure condition for the triangle. And the pure condition for the triangle, you can work this out, in 3 space is just 1. Okay, so in 3 space, the pure condition for the triangle is 1. And so, so then all we have to do is figure out what's the kind of portion of the pure condition that comes from the tie down. And there's a very beautiful theorem in the paper by White and Whiteley that says that that this pure condition for the tie down is a bracket polynomial, and it's measuring when the 6 lines, here the 6 lines are the lines spanned by A and D and A and E, etc. All these green line segments get extended to lines, and when do those 6 lines, when are they dependent in 3 space? Okay? And I thought about this for quite a while. When are 6 lines dependent in 3 space? And I was somewhat despairing of what was going on here. And then I remembered that that about 4 years ago, I gave a talk in a special session. And in fact, I think it was organized by Mira and Jessica Sidman. It was at the SIAM conference in Atlanta. And I had explained there that there was something called the super bracket that I learned from Neil White's survey paper in the handbook. And that super bracket comes up in robotics, and it measures when 6 lines in 3 space are dependent. It was like, oh, great. Let me just look at that super bracket. And so let me show you the super bracket. Oops, there's the super bracket here. It's this crazy bracket expression. So this is a line A1, A2. So A1 and A2 are points in 3 space. B1, B2 is another line, etc. And this symbol denotes a bracket polynomial with 24 terms. So it's a very compact way to write down a very large bracket polynomial. And there's this dotted notation, which if you read various papers in this subject, you'll see dotted notation a lot. What this means is that there's a term here that you can just read off, but you're also allowed to interchange D1 and D2. You're allowed to interchange those, and you're allowed to interchange or substitute E1 for E2 and kind of act using a permutation for those. So you've got 2 permutations here, to each of order 2, and they generate 4 brackets. So this line here really represents 4 brackets. This next term represents 4 more brackets. Here there's 3 permutations, each of order 2. So that represents 8 brackets and 8 more brackets, and that's the 24 terms. Okay, so whew, that's a lot of terms, but we have special lines. We don't have just general lines. We've got AD and then another line BD, so they share a point and things like that. And if you work it all out, it turns out that 22 of the brackets vanish, and so you only get 2 brackets left over. And this is the portion of the pure condition that comes from the tie down. And if you go back to what we were doing before, this is exactly the pure condition for the braced prism. And this agrees then with the table that's given in White and Whiteley's SIAM paper, where they write this pure condition down. So that's a nice computation. And now I want to turn to, like, what does it mean? On one hand, we know what it means. It means that these 6 lines are dependent in 3 space. But I'd really like to get a Grassmann-Cayley interpretation for this bracket polynomial. And this bracket polynomial, remember, is telling us when the braced prism has motions. So okay, back to the polynomial. So we need this polynomial to vanish. So we need these 2 terms to be equal. And so I can divide one term by the other and say, well, that quotient has to be 1. Okay, so that's how we get this set up. And then if you stare at this long enough, I keep saying that, sorry about that, but if you spend enough time thinking about such things, you realize, oh, I could kind of reorder things, and they look kind of interesting here. I've got like ACF appearing in the top, and I've got an ACF factor also appearing in the bottom. And then I've got kind of B and D. And this is, now I'm going to kind of pull out a bit of magic that I learned from Susanna Pell. I learned this in her algorithm for Cayley factorization. And her algorithm is kind of designed for working in P2, in the plane, not in 3 space. But if you generalize the algorithm appropriately, and I claim this is the appropriate generalization, then you can see that what you should be doing is taking this ACF term, which is a plane, right? It's spanned by 3 points, and this BD term, which is a line, and you should intersect that plane with the line. And that gives you a point in 3 space. And you do the same thing for these other terms. And then what we do is we replace this bracket, BACF, with the distance from B to A, so the distance between these 2 points. And you get this product of oriented distance ratios. And notice that this goes from B to A and then from A to D. I'm thinking of this as kind of going from B to D, and you pass through A on your way. And then you go from D to C, passing through B, and then you go from C back to B, where you started, with C on your way. You get a kind of triangular path going from B to D to C and back to B, with these capital letter points on the edges of the triangle. And Appel's algorithm suggests that what you should do is, on this triangle, sorry, I didn't draw a triangle here. On this triangle, you can kind of take 2 of the sides and compress them into one edge, kind of shortcuts. So that's what we're going to do now. We're going to take this portion that goes from D to C and from C to B. We're going to go from D to B directly, passing through a new point, Z. And kind of the magic is to express what that new point is. And so I've written down the Cayley expression for that new point. And then you get this product of distance ratios, which is supposed to be equal to 1. And how could that happen? You're going from B to A divided by A to D, and going from backwards from D to Z divided by Z to B. And this can only happen if Z is actually equal to A. Aha. So A must be equal to this expression, but it's also equal to a different expression. And let's see here, it's equal to this expression. Both expressions, A is on this plane and also on the line BD. Z is on the line BD. So they're both on the line BD. The real question is Z on the plane as well? And so you can measure that by asking whether whether Z ACF, there should be brackets around this, is equal to 0, whether the join of Z with A, C, and F is 0. That can only happen if Z is actually on the plane generated by A, C, and F. And then you can just expand that using this, plug it in here, expand everything out. You get this nice Grassmann-Cayley expression, and then you can actually expand it using the meet and join operations, and I did, and you get minus the pure condition. So you get almost exactly the same polynomial, and certainly up to, vanishing, it's the same. And I should just say, all this is kind of ad hoc. I kind of cooked it up before these lectures, so I don't know how general all this kind of approach is, but I do have to warn you. I put this point in red because it's not at all clear that Z is well defined as a point. We're working in P3, so the ambient space is a 4 space, and C is a point and D is a point. So this is a line, and it's supposed to intersect another line. But in 4 space, 2 lines generically don't intersect. So what's going on? Like this meet should already be 0 here. And the answer is actually this calculation here has to take place in a plane spanned by B, C, and D. And there's ways to make that explicit and even put it into terms of Grassmann-Cayley expressions in 4 space, like coning and other stuff. But I don't want to go into that. I just wanted to point out that we actually have a Grassmann-Cayley expression that explains what the heck we mean when we talk about the 6 lines being dependent. And this actually, I think, is actually part of the challenge of working with Grassmann-Cayley expressions, or maybe I should say with working with bracket polynomials, is interpreting what the heck they mean after the fact is sometimes pretty hard. Okay. Okay, just a few more remarks about Grassmann-Cayley factorization to set us up for Wu's algorithm. So not every bracket polynomial admits a Grassmann-Cayley factorization. So it's possible that my efforts before were futile. It turns out they weren't, but I was trying to factor this pure condition, and it might not have had a Grassmann-Cayley factorization. Here's a simple example that I got from Appel's thesis, but she cites an example, I think, due to White, which says that this simple bracket polynomial doesn't admit a Grassmann-Cayley factorization, but if you multiply it by a little, by another bracket, then it does. And in fact, that's kind of the general behavior that occurs. Walter and Bernd-Sternfels proved that if you start with a bracket polynomial, then that bracket polynomial may or may not factor as a Grassmann-Cayley expression, but there's always a bracket monomial, so that you can multiply by, say, the product of a bunch of brackets, M, multiply P by that, and then you do get a Grassmann-Cayley factorization. Okay, so, and the way I'd interpret that is saying that the bracket condition that the bracket polynomial P vanishes is equivalent to a Grassmann-Cayley expression under the side condition that says that M is not 0, right? And that side condition is particularly simple because it's just saying a bunch of brackets themselves aren't allowed to vanish, and they would only vanish in a degeneracy situation where kind of 4 points lay on a plane in 3 space, that kind of thing. So it says that if you're trying to interpret this bracket polynomial, at least up to some non-degeneracies, you can write it down as a Grassmann-Cayley expression. Now to actually do that algorithmically and kind of produce it isn't so easy. Maybe that's it's very hard, actually. Maybe the better way to say it. And this same thing with these side conditions happens also when we use those binomial proof techniques. It didn't show up in the example that I showed you guys last time, where you multiply the 2 kind of bracket polynomials down the left side and down the right side and set them equal, cancel the polynomials. But sometimes it does turn out that that you have to say, well, some of these brackets aren't allowed to be 0. Otherwise, you can't cancel them. Maybe that's the best way to say it. Okay. So let me shift gears and say something about Wu's method. So this is my first time hearing about Wu's method in this class. So I learned about Wu's method in this class and in preparing for these lectures. And I should say right at the outset is, that makes me a neophyte in terms of Wu's method, and I found it a bit heavy going. I found several papers on Wu's method in the literature, and it's a bit unfortunate. There seems to be situations where people kind of skim over the details, and so you don't quite get the full sense of what Wu's method is, or they go into all the details, and sometimes in language that isn't quite common in commutative algebra, at least. So I found the reading somewhat heavy going. I'm sure this is just my kind of lack of understanding, but I'm going to try my best to explain what Wu's method is for you. So Wu's method is a technique for proving statements in elementary geometry. So that's what we're interested in. And the approach is really kind of appealing. He uses polynomials to encode the hypothesis of each hypothesis of a geometric statement. And he uses a polynomial C to encode the conclusion of a geometric statement. Okay, so you've got these hypotheses polynomials, H1 through HT, encoding the hypotheses, and then a conclusion polynomial C encoding the conclusion. And if it turns out that whenever you have the hypotheses vanishing, then the conclusion also vanishes, then that would prove your theorem, right? So there's a technique then in algebraic geometry to check whether this variety cut out by the vanishing of these hypotheses polynomials is contained in this hypersurface. Okay. Well, in commutative algebra, we'd say, well, this happens precisely when C is in the square root of, the radical ideal generated by H1 through HT. And here I'm assuming that that we're working over an algebraically closed field. Okay, and that just means that some power of C is in this ideal generated by H1 through HT. So that's kind of what we're checking. And in my reading of Wu's method, people don't actually use this power. I've not seen anyone use this radical. Instead, what they do is they try to aim to show that C itself is in the hypothesis polynomial. And certainly, if that was true, then you would have this inclusion, and C equals 0 would follow from H1 through HT being 0. But that's just what they're aiming for. They actually usually fail to get that, and they get something slightly weaker. And what they prove instead is they find a polynomial G, so that G times C is in the ideal, H1 through HT. Okay, and so as long as G evaluates to be non-zero, then the theorem holds for the geometric situation that's parameterized by x1 through x1, x2, all the variables. Okay, so this is like a side condition. G represents a side condition saying, as long as that side condition isn't satisfied, you can think of it maybe as non-degeneracy, then the conclusion follows from the hypotheses. And so this is analogous to what we were just talking about side conditions in Grassmann-Cayley factorization and in binomial proofs. Okay, so let me do one example just to show you kind of what I mean, because I sketched out the method, but I didn't really give enough detail. So, so we're going to look at this theorem. It says that if you have a parallelogram, ABCD, then the intersection of the two diagonals, AC and BD, intersecting at point O, then then O is equidistant from A and from C. Okay. So it's a pretty simple geometric statement, but what we do is we start assigning variables to coordinatize the various points. So B gets a pair of coordinates. Bear with me for a moment. The labeling seems totally nuts, but there's a method to the madness. B gets a pair of variables, C gets a pair of variables, A gets some, D, etc. So everybody gets their own variables, and then we notice that, hey, the theorem itself is actually invariant under translation and rotation, right? Doesn't matter if we use a rigid motion, it doesn't change the theorem. So we could use a rigid motion to kind of tie down A and put it at the origin, 0, 0, and tie down B so that B is on the x-axis, let's say, right? And so a bunch of these terms disappear, or at least become 0. Excuse me for a moment. So here, and now you've got this picture. A is 0, 0, B is U1, 0, and C is U2, U3, and D has got X's and O is X's. Okay. So now let's look at trying to encode the hypotheses, right? I want to encode that AB is parallel to CD, that these two sides are sides of a parallelogram, so they should be parallel, right? And one way to do that is to calculate the slope of AB, 0, and make sure that the slope of CD is also equal to 0. And if you do that, you get this polynomial here, the H1. Okay. Similarly, you can check that AD and BC have the same slopes and encode that using a polynomial. You could ensure that O lies on BD. You could do that, say, by calculating the slope of BO and then calculating the slope of BD and saying, hey, they have to be equal. Okay. And similarly, O lies on AC. And then the conclusion polynomial is saying that the distance from A to O is equal to the distance from O to C. And you get those just by the usual sum of squares. And we'll write that down. Okay. So that's our conclusion polynomial. And you'll notice that that the polynomials have this nice property that the first polynomial only involves x1, the second polynomial involves x1 and x2, and what I was kind of hoping for was that the third polynomial would involve only x1, x2, and x3. That we would have essentially some kind of triangular system here in the x variables. And that's not the case, but we could make it the case. So that's the next thing. So the next step is that typically the hypotheses you write down are not triangular in the sense of only adding one more variable each time. But what you can do is you can, for instance, there's an x4 in both of these two polynomials, h3 and h4. And so I could essentially use one of the equations and substitute for x4. Or a different way you could say it is, say, take this leading coefficient of h4 and multiply it by h3. Take the red leading coefficient for h3 and multiply it by h4. And now they have exactly the same leading coefficient in terms of x4. And so if you subtract the two polynomials, you should get rid of the x4s, right? And that could become our new h3 with kind of x4 removed. Okay, so that's gives us this triangulated system. Still look over the equations, but the main thing that you're supposed to be getting here is that these you've got this kind of triangular system with you adding one variable each time. Okay, and then so I've kind of shown you one way to try to triangulate a system using this kind of substitution, if you wish, or you could think of it in Grosvenor bases. We would have called this an S polynomial. We did a computation like that. But unfortunately, it turns out that you can't always triangulate a system like this. You can write down systems that you can't triangulate using these techniques. And instead, what you might have to do is factor some of these polynomials. So for instance, if you had x4 appearing to the second power here, then you might be in a situation where you're kind of like, oh, I have to substitute for it, I'd have to solve for x4. And that's not so easy. I'd like to try to factor this polynomial, and factoring that polynomial in x4 means factoring over an extension field, say of the reals, by all the other variables. So you're working over a field and you're trying to factor polynomials, and all of a sudden you get into complicated territory where we're doing kind of sophisticated questions in algebraic geometry, really, about whether certain varieties are reducible or irreducible over the reals. Pretty complicated stuff. Just so it's not so simple in those cases. So I'll just say that if this variety is not irreducible, then you're going to fail to triangulate, and then you have to factor and consider each of the components in this variety separately. And that becomes complicated. Okay, but we managed to triangulate. So what do we do next? So we'd like to reduce the conclusion against each of these hypothesis polynomials. And essentially the idea is you're going to use H4 to get rid of the X4 in the conclusion, H3 to get rid of the X3 in the conclusion, etc. H2 and H1, they're all going to kind of get rid of the X's. And eventually you're just going to be left with a polynomial, hopefully in the U's. And that polynomial, if it's non-zero, then your theorem just isn't true. But if it is zero, then your theorem is proved. Essentially, you've shown that C is a polynomial combination of H1 through H4. Actually, there's a little bit of this side condition business as well. So let me just show you that. How do you reduce C? Well, here's C. And what you do, we're going to try to use H4 to reduce C. And so H4 has the X4 in it. So I'd like to kind of get rid of the X4 in C using a reduction. So what am I going to do? I'm going to multiply C by this blue leading coefficient of the X4. And I'm going to subtract this red leading coefficient of C times H4 from the resulting polynomial. So I take minus U2C, and if you wish, you can kind of expand minus 2UC as a copy of 2U3H4. So I've taken a copy of this multiple of H4, and these two polynomials have the same leading term. So this contributes something to the polynomial C, and then there's some kind of remainder. And the remainder doesn't involve any X4s, which is very nice. In fact, it's this remainder. And then you would kind of try to further reduce the remainder term here using H3. You get rid of the X3s at the potential cost of substituting some X2s into the problem, or X1s. Then you get rid of the X2s using the H2, and then you get rid of the X1s in the final remainder by using H1. And what we'll do each time is multiply C by one of the leading coefficients, by the leading coefficient of the of one of the hypothesis polynomials. And in fact, here things are a little simple. You only have to multiply by the leading coefficient once, but in some situations where X4, for instance, appears to a higher power, you may end up having to multiply multiple times by the leading coefficient. And this whole algorithmic setup is I think due to mathematician Ritt. And one complication in all these things, which I haven't really spelled out here, is that we're working over the real field here. We're not working over the complex numbers. We'd like to be able to work just with real setups, and so algebraic geometry over the real numbers is its own complication, its own complicated kind of body. And I'm just going to refer you to Faye's lectures next week about that. So what do you do now that we've reduced C? Well, you finish the reduction. So after you've reduced C, you've got leading powers of leading coefficients of the various hypotheses polynomials. Not sure what the 4 and the 1 here are doing. Sorry about that. Times C, and this is equal to a polynomial combination of the hypotheses plus some kind of remainder term. And then the point is that if the remainder term is 0, then you've got exactly what you wanted. You've got this G over here times C is a linear combination of the H's. And so C should be 0 when the H's are all 0, at least subject to the leading coefficients here being not 0, the leading terms. I guess I should call them the leading coefficients, really. The leading coefficients are the side conditions. So if this remainder is 0, and it is in our example, then your theorem is true, subject to these side conditions. And if it's not 0, then your theorem is actually generically false, is my interpretation of that. So, this works pretty well for simple geometric statements like the one that we were just working with. But there are some complications, and some of the complications involve, for instance, problems triangulating the system. And in that kind of situation, you may end up having to do significant amounts of computation to kind of reduce the hypotheses to appropriate subsets that you then have to verify the condition over each of the components of the hypotheses, variety, etc. So it's a kind of complicated thing, potentially. But when it works well. That's what I'll say. There used to be an advertisement for certain beer in the Maritimes in Canada, and they said, "Those who like it a lot." I'm not sure exactly what that was supposed to mean, but I would say that when Wu's method works well, it works really well. When it doesn't work well, should maybe look for a different method. So, okay, that's what I had to say about Wu's method. Mary, you probably had some other ideas about what should be said about Wu's method.
Well, yeah, this an example or two would have been good, but you didn't have time. It's okay. The other thing was this idea of the characteristic set thing, the triangular set, whatever. Maybe we might have some time to look at it. Maybe later at some point.
So are those these given by these triangularizations, like
yeah, I think
are they the leading terms of
this went out a little fast for me here to parse the variables and stuff, but
okay, we'll talk about it at some time. That would be fun. I'd like to understand more about Wu's method.
Okay, we'll do that.
Cool.
Yeah.
Okay. So that's the end of what I had to say. Thank you for the time, and thanks for giving me the chance to talk.